Okay, this is video number 21. And this is chapter 4, section 4. And this is all about graphing log functions. I don't know how long this video is going to take, but I feel like it might be lengthy. So if you want to pause and do anything, get ready for this, be prepared. All right. First thing to note is that exponential and log graphs are inverses of each other. Where g of x, this will make more sense after we actually plot them, is a reflection of f of x over the line y equals x. So we're going to make f of x our exponential, and we're going to make g of x our log function. And we're going to actually graph these out and see how they're going to look here. So if you have graph paper, this might be really handy. If not, because I actually put some in my notes. If not, you may want to draw out a pretty accurate coordinate plane. I'm going to pop one into my drawing here. All right, so what we're going to do here is we are going to actually graph f of x is going to be the exponential function 2 to the x. And what we're going to do is use an xy table. And we're going to put in the points 3, 2, 1, 0, -1, -2, and get the y's out of here. Now, keep in mind what we're actually doing here is we're doing things like 2 to the 0, right? The x is our exponent. So if x is 0, that means 2 to the 0 equals 1. And that's our y value. 2 to the 1 is 2. 2 to the second is 4. 2 to the third is 8. So we're getting ordered pairs out of this. 3, 8. 2, 4. X and y, right? 2, 2. Let me scoot that little coordinate plane over just a touch. This one's 0, 1. What happens when we put a negative in? If we have 2 to the -1, well, I'm going to pop this over here. 2 to the -1 is the same as 1 over 2 to the first, which is a half. That's using our powers of negative exponents. So this is a half. So we have -1, a half. And then if we put a -2 in, we have 2 to the -2nd, which means 1 over 2 to the second, which is, 1/4. So 2 to the -2nd is 1/4. So this becomes -2, 1/4. Okay, so those are the ordered pairs that we're going to use. And I'm going to plot our exponential function here in a blue pen. All right, so we don't go quite up to 8, but we've got 3, 8. That would go just off the graph a little bit. 2, 4. Oh, look what I did here. This should be 1, 2. 1, 2. And remember, when we did exponentials, we said all exponential functions, just as a quick reminder, they all go through the point 0, 1, and they all go through the point 1, the base. And in this one, the base is 2, right? So this should go through the point 1, 2. And then 0, comma 1. That's why they all go through the point, because anything to the 0 is 1. Okay, and then we have -1, 1/2, and then -2, 1/4. And at this point, we're getting really close to the x-axis. So I'm going to draw in my curve here, which is going to look like this, and it will approach but never touch our, in theory, never touch the x-axis, right? Okay, well, check this out. Because these are inverses, I don't know if you're aware. So again, depending on where you came from last year and what you know about graphs, if you have inverses in graphs, then the xy from one graph becomes yx in the inverse graph. So what we're going to do here, I wish you could see a little bit more on this at the same time. Our inverse is going to be g of x. This is going to be our log function, is going to be base 2 to the x. And what we're going to do is we're just going to take all of these ordered pairs from the exponential table and we're going to swap them around. So 3, 8 is going to become 8, 3. 2, 4 is going to become 4, 2. 1, 2 is going to become 2, 1. 0, 1 is going to become 1, 0. -1, 1/2 will become 1/2, -1. And -2, 1/4 will become 1/4, -2. Now, with the exponential, we made this statement. They all go through the point 0, 1, and 1 base. In a log, they're all going to go through the point 1, 0, because this will get switched around because of the properties of inverses. And they're all going to go through the point, the base, which this is the base, comma 1. All right, so let's plot some of these points. We have 8, comma 3. Well, that's going to be off our graph just a little bit. It will be off to 8 and up, off 8, up 3. And I can't really plot that. It's too far off. So we'll go 4, 2. That's going to be there. 2, 1. It's going to be there. 1, 0 is here. 1/2, -1. And then 1/4, -2. So this guy, let's see. Oops, I want to undo that last little piece. Okay, so I know at 3 I'd be out at 8, so this is going to be pretty flat here. And this is going to come down and go like this. So this is g of x. That's the log graph. And this guy is f of x. It's our exponential. And then there's a statement up here in the notes, let me go back to it, that said g of x at the bottom is a reflection of f of x over the line y equals x. Well, I don't remember how much you remember about the line y equals x, but that's in the form y equals mx plus b, where b is 0, which means it would go through the origin. M is 1 because there's no value in front of the x, so this would have a slope of 1. And that would be a dotted line that would go that way, so we could sketch that line in. Nothing was working. I don't know where my pen went. Okay, so this whole chapter is about the logs, the purple graph on the bottom. So they're going to point down and over to the right unless there's a transformation. The exponents pointed left and up unless there's a transformation. But you should know that they're inverses of each other. They are reflected over that line y equals x, and that they have some of these similar properties. So this point here, this point 0 or 1, 0 is going to be in all parent graphs unless there's a transformation, okay? We're also, because our base is 2 here, we're going to have 2, 1. This point would be on this graph. If we had a base of 4, then 4, 1 would be on the graph. If we had a base of 6, then 6, 1 would be on the graph, right? So we know that we can expect some things to happen based on that. Also, just a reminder that, and I kind of mentioned them last time, but not such a huge thing, this graph comes down here and hits what's called an asymptote. And you're going to have to find these asymptotes in this one. So we're going to talk about that later on in this chapter. All right, next. I think I hit everything else on that page. Flip my page here. It might be a little noisy. All right, remember that this is chapter 4, section 4. I got a pen. So this is 4.4 in your notes. And let's flip the page for me. So some more information. If we have the graph f of x equals log base 6 of x, then this we know, a couple things. This is going to go, I don't know why that's jumping around on the screen. Then this is going to hit the point 6, 1, 1, 2, 3, 4, 5, 6. So we know that this guy's going to go through the point 1, 0, and then out at 6, up at 1. So this graph would look something like that and have a pretty aggressive turn to it. Okay, and we know these points because of some information that we can gather about any parent function, right? They all go through the point 1, 0. They all go through the point base comma 1. And remember, this is the base that you're looking for. Well, here's some other information. The domain of all of these things are 0, comma, infinity, right? They don't use any x values in the negative part of the x-axis. Nothing over here is being used. Only the positive values of x. So 0 to infinity. The range values, well, you're going from negative to positive infinity. All right, your x-intercept is always going to be 1, comma 0, unless there's a now this is if there's no transformation made anywhere, right? Your y-intercept, I don't know if that's going to be asked in varsity, but don't fall for it. There isn't one. I was going to say there is not one, and then don't worry about it. Never mind. That's D&E. That's what you would put into varsity. And in this case, you have a vertical asymptote at x equals 0. Remember, all vertical lines are x equals something. So in this case, you have a vertical asymptote at x equals 0, right? So whatever you, and those are usually drawn into a graph if you need to draw them in as a dotted line. I don't have you do a whole lot of graphing in here. So just so you know. All right, and then here's another just little statement. These are true unless there is a transformation. Then the domain may change. And we'll talk about how to find that, but the range will stay the same. Okay? All right, so the next statement that you need to have is, this is about transformations of log graphs. And the rules for these are exactly the same as exponential graphs. So I'm not going to list those again. That's just silly. I want you to go back to 4.2 where we listed those all out before. And here is the general statement that you're going to use. The function changes a little bit. We have f of x equals the log base a of x plus c plus b. And so if you remember, here, I'll flip my page a little bit and I'll read some of these. If a is negative, the graph is reflected about the x-axis, so that would be the base. The b value out here on the end shifts the graph vertically in the direction of the sign. If it's positive, it goes up. If it's negative, it goes down. Same thing here for the log function. The c value inside the parentheses shifts the graph horizontally, left or right, in the opposite direction of the sign. So if it's positive, it goes left. If it's negative, it goes right. And we stated all of these. I'm reading them literally out of 4.2. Number 4, in this case, if the exponent was negative, then the graph is reflected about the x-axis. Well, I do have something here. Let's see. In our case, these two things flip it about the x-axis. So these are the same. The log function is flipped in one of two ways. So you could see this written either of these ways. It could look like this. Negative log, I wrote that wrong. That's supposed to be a 4. Negative log 4 of x is exactly the same as log to the 1/4, that's the base, of x. Okay, so get rid of this dumb thing, that box. All right, so this will flip the log function about the x-axis, which means it's going to be flipped upside down and look more like an exponential. And this, they will look identical to each other. Okay, so if you see one like that in varsity, you're going to want to make sure that you're using, I think I used this guy in varsity. All right, so let's see a couple of examples of this. So let's get a different color pen, purple. All right, log base 4 of x minus 1 shifts this 1 unit to the right. Right, because what's changed is the c inside the parentheses, and those get shifted in the opposite direction of the sign. How about this guy? Log base 4 x minus 1. No parentheses, which means it has no c value. It would be 0. So that minus 1 is a b, which is a vertical shift. And those get shifted in the same direction as the sign. So this gets shifted 1 unit down. Okay, because that's a b value. How about a combo of the two? If you see this, log base 4 x plus 1 minus 1, this is going to shift 1 unit, 1 unit left, and 1 unit down. Okay, so you can have a combo of those things. All right, let's talk about domain and range. Now you're going to have to find domain and range for a few of these. I don't know that I actually need to take you to varsity and show you what they're going to look like. I'll just kind of work them out here. So we'll do an example. Given the natural log of 3 minus 2x, state the domain and range. Okay, so here's what you're going to do first. You need to find the vertical asymptote to find the domain. And how you're going to do that, you're going to set the x plus c equal to 0. Now, recall that you're working with the log base a x plus c plus b. So what we're talking about is the part in parentheses getting set equal to 0, okay, in order to find that thing. So we're going to set that equal to 0 and solve. Okay, so for this problem, here's our problem that we're given the natural log of 3 minus 2x. So we're going to take the x plus c is the part in parentheses. So we're going to take 3 minus 2x, set that equal to 0. Move over the 2x, so we have 3 equals 2x. Divide both parts by 2, and you have x equals 3 over 2. Okay, just kind of hang on to that for a minute. And now what you're going to do is you are going to go to Desmos, and we are going to actually graph that function, 3 minus 2x. So let me throw my keyboard on here, and we will go do that. So my mouse isn't working. Here we go. Okay. Let's go to Desmos, graphing calculator, and we need the natural log. So you're just doing ln parentheses 3 minus 2x. And what you see is the graph there. And the asymptote, you can tell that there's a straight line, almost basically straight down the graph. That asymptote that we found, let me just move this a little bit. You found x equals 3 over 2. That's 1 and 1/2, right? 3 halves is 1 and 1/2. That's the value of the asymptote. It's at 1 and 1/2. So what you need to find is your actual domain. Well, if you were to scroll over in Desmos, you're going to find that this graph goes forever and ever and ever and ever over to the right, towards negative infinity. And basically the graph ends at the asymptote. Okay, so I want you to have a picture here. Now I'm going to go back and actually make a statement over there. And here's what that statement is going to be. So we'll change the color here. Oh, how did we change screens? All right, so your domain, this is kind of a note. Your domain will go from negative infinity to an asymptote or from an asymptote to positive infinity. Okay, so your domain will either look like, in our case, we know the graph looked like this. So we're going to go from negative infinity to the value of the asymptote at 3 halves. So this is our domain. Okay. Your other option is the graph went the other way. So it would go from 3/2 to infinity. All right. So it's going to be one or the other of these. All right. And then the other thing it asks you for is the range. Well, the range of all of these are negative infinity to infinity. So that's kind of a no-brainer. No work needs to be done. You just have to list that. Okay. All right. The next problem. You need to state the domain and a vertical asymptote. Oops. I was writing on the screen with my hand. And I have my keyboard attached, so I'm trying to shortcut things here, and look what's happening. Whoop. All right, so new screen. Bear with me, please. So we're going to state, oh, geez. No, I can't bear with myself. State the domain and vertical asymptote for f of x equals the negative natural log of 2x plus 3 plus 4. Now, again, all that we care about is this part right here. The rest of this function doesn't really matter until you actually graph it. So we're going to take that and set it equal to 0. And you should be able to pretty much do that in your head. Okay, so that's negative 3/2. And then we're going to go over to Desmos, and we're going to change this guy a little bit. So we're going to throw a negative in front of there. You can see it flips it upside down. And then change this. All right, so we have 2x plus 3. And then there was a plus 4 on the outside. But that's just going to be a vertical shift. Okay, so there's that graph. We found, take a look, I'll scroll it back down. Vertical asymptotes at negative 1 1/2, negative 3 over 2, negative 1 1/2. So this time we're going from the asymptote to the right towards positive infinity. Okay, so that's going to be our domain. So I'm just going to minimize that. So our domain here is our asymptote to positive infinity. And the vertical asymptote is x equals negative 3 over 2. It's exactly what you got right there. Okay? All right. I don't really think I need to do another one of those. I had one more example, but we don't really need to go that far, I don't think. All right, the last thing then is end behavior. Let's talk about that, and then we're all done. End behavior is the end behavior describes the behavior of the graph of a function at the ends of the x-axis. Okay, and then I actually am going to add specifically what we want to know is, what is the y doing? Y going, and it's either going positive or negative infinity. Okay, so those are the only kind of answers you're going to have to these problems, positive or negative infinity. So here is how one of these problems is going to look. Here's the problem. I'll type that out in black. So it'll say what just happened? I keep hitting things. Oh no, what did I actually hit? Okay. It's going to say given f of x equals natural log of x minus 4. And this is what's going to be printed in varsity. As x goes to 4, that's what that arrow means. As x goes to 4, then f of x, and remember that means y, then y goes to, and they'll have a box. And then as x goes towards infinity, f of x goes towards, and a box. Okay, so what we're going to do is we're going to go graph this and see what happens as x goes towards 4 and as x goes towards infinity. So let's go do that. So we're going to pop over here. We're going to change our function. So we have the natural log. This was x minus 4. All right, so here's the graph of the natural log of x minus 4. And we can see it's moved over a little bit, right? There's our actual xy origin. So what is happening? As x goes towards 4, what is y doing? That's this question right here. Okay, that's what that question is saying. As x goes towards 4, what is y doing? Well, as x goes towards 4, I don't know if I can write on the Desmos part. No, I can't. As x goes towards 4, that's right here. What is y doing? Well, y is going down, right? Y is going down as x is coming towards 4. So what we're going to put in there, remember, your y answer is only going to be positive or negative infinity. Well, as we approach 4 on the x, this thing's going straight down. So this is going to be a negative infinity answer. Okay. And then what's the other question? So the first one's going to be negative infinity. And then as x goes towards infinity, well, that means as x goes towards positive infinity, as it goes towards the right-hand side of the graph, what is happening? Well, you can drag this over. It's just going to keep on going and going and going. And you can see, I mean, yes, it's going pretty much to the right, but it's in the positive quadrant for y. So it's going up very slowly, but it's rising up. So it's going towards positive infinity on the y as well. Okay, so as remember, so I'll draw a little graph here. This is kind of what was happening. So as x was going towards 4, this guy was dropping down. The y part was dropping down towards negative infinity. So that's what's going to go in here. And as x is going towards infinity this way, that's actually going towards positive y. Remember, these mean y also, right? F of x means y. So this is saying, what is y doing? Y is going towards positive infinity. Okay? I have 2 more examples of those, and then that will be enough, I think, for you to be able to do your assignment. All right, so let's scroll down a little bit. Scroll down a little bit. So the next one, graph negative log 2x plus 3. And then as x goes towards negative 3 halves, and they had that in parentheses in varsity, then f of x goes towards a box. And as x goes towards positive infinity, f of x goes towards a box. All right, so we'll make a little graph so we can come back and sketch it. And we're doing negative log of 2x plus 3. Let's go. Negative log of 2x plus 3. And this was a negative. Oh, this was an log also. That will change a little bit. So negative log of 2x plus 3. All right, I'm going to drag back over here. Okay, so here we go. So I'm just going to sketch that, and then we'll talk about it where I can draw on top of it. All right, so let's go in kind of like this jobby. All right, so this is saying as x is going towards negative 3/2, so that's negative 1.5. So that's happening over here. Well, where is y going? Well, as x is approaching negative 1 1/2, y is, this one's pretty easy to see, going up towards infinity. And as x is going towards infinity, this way, what is y doing? Well, y is going further and further and further down. So that guy is going towards negative infinity. And actually, if this helps you, I don't know, this may help if you think of this in quadrants. Let me change the direction. So this is going towards positive infinity on the x. This is going towards negative infinity on the y, right? And I mean, if you think of these, all of these, this is going towards positive infinity on the y, negative infinity on the x. So if you have something in this quadrant, you can write it as an ordered pair. Remember, any ordered pair is x, y. So this, anything in this area, whether it's slightly up here, slightly down here, it doesn't matter where it is. It's going to be a combination of the x and the y. So if you're looking at the y, you know it's going towards negative infinity because it's in that quadrant. Okay, so you can think about that way. And we did some of that in the unit circle as well when we were talking about those. All right, so that's how that one would look. And then one more. We have, let's go back to black. If you had the log of 3 minus 2x plus 5, it says as x goes towards 3/2, f of x goes where? And as x goes toward, as x goes towards, this time it's negative infinity. Again, righto. As x goes towards negative infinity, f of x. So we're not always going to infinity here. Sometimes we'll go towards negative infinity. Where is that one going? All right, so log 3 minus 2x plus 5. Let's go see. So this is a positive log, so we'll get rid of that guy. I need a log back in there. All right, and we had 3 minus 2x. And then plus 5. All right, so there's an example of what that graph looks like. So again, I'll go back and sketch it. So we have this kind of in that direction, right? So again, if we go with this whole idea, if you wanted to know where that guy's pointing, this guy, and I don't know which one we have to focus on yet. Positive, negative. This guy, the x is negative, the y is positive, right? So we can just kind of focus on where we got to go. All right, as x goes towards 3/2, that's out here. That's this guy. 1, 2. Here's the 3/2. We know our y is going down. Okay? As x is going towards negative infinity, as x is going towards negative infinity, then our y is going towards infinity. All right, and that might be, if this is easy for you to draw out those pairs, depending on which way your graph is pointing, you can do that. All right, so again, we'll make sure you're labeling on your paper. That's 4.4. This is the end of this video. I am sorry this is probably long. I have no idea. I have no counter anywhere on here, but hopefully it's all good. Toodaloo.